folks. In this lecture, we delve into the fundamental kernel of scientific information called a measurement. A measurement has two important pieces. The first part of the measurement we identify is the unit, which dictates the type, standard, and scale of the measurement. The second piece of the measurement is the number, which tells us how many units were used in the measurement and contains the vital information of how precise the measurement was conducted. Now, in this talk, we're going to concentrate and focus on the unit part of the measurement.
A unit tells us what we are measuring and something of the scale or size of the thing we are measuring. The process of choosing a good unit is complicated by the fact that there are multiple flavors of units to choose from and many different standards. In the past, the British system of the English units was the standard used by most of the world. This classification morphed into the imperial system and finally into our U.S. customary system. The use of these systems has been minimized in most parts of the world except for the Caribbean and backward nations like, well, the United States. The most prominent system used by scientists is the System International of Units, or SI for short, a modern revision of the metric system. A system of measurement utilizes a limited set of base units. The units for time, length, mass, and temperature are the more important ones we use in chemical measurements. Both US and SI systems share the same definitions of time, the second. For length, mass, and absolute temperature, the US customary system uses the yard, pound, and Rankine units, whereas the SI system describes these quantities with the meter, kilogram, and the Kelvin, respectively. The SI unit is now so entrenched as the worldwide standard that the U.S. customary systems of measurement is dependent on the SI for the formal definition of the yard, which is now defined as 0.9144 meters exactly, and also the pound, which is defined to be exactly 0.453592237 kilograms. The second important aspect of the unit is that it represents the size of the measurement adequately, and this requires us to scale the base units to the size of the thing we are measuring. It seems silly, right, to represent the diameter of a penny in the units of miles when it would be better served to measure it in inches. Unfortunately, in U.S. customary systems, you have to memorize a load of different names for a range of different sizes for each measurement type. For example, for length, we have an inch, foot, yard, chain, furlong, and mile. And for weight, we have grain, dram, ounce, pound, stone, hundredweight, and ton. The SI system is much simpler in that it uses a common prefix multiplier to scale any unit of measurement. An extensive table of these SI prefix multipliers is shown. Again, we don't care what the unit of measurement is since we can scale it to any size we require using the prefix multipliers on the table. For example, we use a base unit of a byte to describe a piece or unit of computer data, but we use gigabyte or terabyte units to scale the base unit of a byte to a size that's adequate for buying RAM chips or computer hard drives because the byte is too small to measure the vast amounts of data these pieces of hardware represent. Two of the most common prefixes we will see in basic chemistry are kilo, which multiplies the base unit by 1,000, and milli, which multiplies the base unit by 1/1000th, which is the same as dividing the base unit by 1,000. How about the unit we call volume? Well, volume is one of the myriad of units that are derived from the base units. We picture volume as being a container such as a cube, with the volume being defined as the measured width times the measured height times the measured length of the container. What we do mathematically with the numbers of these dimensions of width, height, length, we also do with the units. So the unit used for volume is defined as length cubed. The two common units used for volume are the milliliter, which is equivalent to a centimeter cubed, and a liter, which is equivalent to a decimeter cubed. But the SI base unit for volume is actually a meter cubed, because the volume is a derived unit of the actual base unit of length, the meter. There is no SI base unit for volume, just length. Also, don't fall into the trap of thinking a meter cubed is equivalent to a liter and that a liter is a base SI unit. It isn't. 1 meter cubed is actually 1,000 liters. There are also many derived units we use in chemistry other than volume. For example, our measurement unit for pressure is based on the fundamental SI units of kilograms per meter second squared. This unit set is called a Pascal. And another derived unit is used for energy, which is based on the derived SI units of kilograms meters squared per second squared. This unit set is called a joule.
In summary, a measurement is made up of a number and a unit. Now, we'll use primarily two base unit systems in chemistry measurements, the US and SI systems. The SI system, along with its multipliers, tends to be the one favored in chemistry. Now, we want to use units that best represent the size of the thing we're measuring. And finally, we want to describe other measurements using derived units, which are really actually just mathematical combinations of the base SI units. All right, that'll do us for now. See you soon.